Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last class we started deriving the modified partial differential equations, and as we discussed, basically when you apply a numerical scheme to a differential equation, you get a discretized equation. And then if you look at the discretized equation closely, basically the leading truncation error, and if you put the temporal form into the spatial form, you would see that the equation that we are solving using the numerical scheme is actually different from what we intended to solve, basically the physical differential equation or the mathematical model. So, today we will continue that discussion. We will look at the modified partial differential equation or MPDE for some more equations and try to find out what basically the MPDE tells us about the stability of the scheme. Okay. So, we had started with the discussion with the consistency of the equation, and we had said that if the difference if the truncation errors go to 0 as your delta t and the delta x, basically the time steps and the spatial grid size goes to 0, then it is a consistent scheme. That also means that my partial differential equation and my finite difference approximation to that scheme are basically consistent. Okay. So, let me just revise this for you briefly. Okay. So, we are looking at the convection scheme del U by del t plus C del U by del x equal to 0. So, this is my PDE. Okay. And let us say if you are using an FTCS scheme, okay, so then this will become UI n plus 1 minus UI n by delta t plus C UI plus 1 n minus UI minus n by delta x is equal to 0. So, this is my finite difference scheme equation. Okay. So, this is my partial differential equation and this is your finite difference equation. Or discretized equation, right, by using the approach which is FTCS. You apply the FTCS scheme, FTCS is our numerical scheme, we apply that numerical scheme to our PDE that we want to solve, and what we get is a finite difference equation, right. So, the consistency of the scheme says that as the delta t and delta x goes to 0, your finite difference equation should lead to the partial differential equation, right. That is what the consistency says, that as you decrease the delta t and delta x all the way to 0, right, your finite difference equation should basically become the PDE or approximate to PDE, right. So, in order to see that, what you can do, you can take the difference between FDE minus PDE, right. So, this is my FDE and this is my PDE, right. And as we know from our earlier classes, that the difference between the two is called the truncation error, right. So, let's look at the FDE. Okay. So, remember our Taylor series expansions, U I n plus 1 is equal to U I n plus delta t U T I n plus delta t square by factorial 2 U T T I n and plus delta t cube by factorial 3 U T T T I n plus all higher order terms, okay, where UT represents the derivative with respect to time. and similarly ui plus 1 n will be ui n. So, we are basically you may have, so this is your I and this is your n, right. So, this is your I and n. Okay. So, you may have points above, points below, left and right, but we are expanding all of them with respect to I and n, right. So, this is basically ui n delta x ux I n plus delta x square by factorial 2 ux x I n plus delta x cube by factorial 3 u x x x I n. Okay. And similarly, you will have ui minus 1 n is equal to u I n minus delta x u x I n plus delta x square by factorial 2 u x x I n minus delta x cube by factorial 3 u x x x I n, right, and plus other terms, right. So, our f d is what? F d is u I n plus 1 minus u I n by delta t plus c u I plus 1 n minus u I minus 1 n by delta x, right. So, use these relations. So, what we will do, we will take these two left minus right and divide by delta t. So, that will give us this term, and then we subtract this minus this, okay, I plus 1 minus I minus 1 and divide by delta x, that will give us this term. Okay. So, let us start writing those terms. I will write the temporal in red and spatial in blue. Let me write it here. So, that will become UTI. So, I am dividing it, subtracting this minus this and dividing by delta t. So, that will become UTI n, okay, and plus delta t by 2, factorial is basically anything but 2 UTT I n, right, and plus other terms. I am not writing the other terms, and then the spatial term will be C and ui plus 1 and ui minus 1 and divided by delta x. So, this will cancel out, okay. When you subtract that, so this will cancel out, and basically this one also will cancel out, okay, and this will be 2 delta x, okay, because this is central differentiating scheme, okay. So, once you do that, this will become C u x I n, and then you will have this term coming up, okay. So, if you, this will be 2 divided by factorial 3, that will be 1 by 3, right. So, this will be plus delta x cube by 3 u x x x I n, and plus you will have ordered delta x to the power 4, right. That will be, this is will be delta x square, because you are already dividing by delta x, and this entire thing will be equal to. So, this is our FD definition, right. So, you can rearrange it, okay, and if you rearrange it, this will become UTI plus CUXI, okay. I have collected this term and this term, and then plus will be delta t by 2 UTTIN, and plus you will have terms which are basically order delta t square and delta x square, right. This all I am clubbing as delta x square, right. So, now our task is to get the truncation error. So, let us represent it by epsilon t. So, the epsilon t is nothing but FDE minus PDE, right. So, this is your PDE. So, if you subtract that, that will become basically, so this FD minus PD if you will do, that will become delta t by 2 UTTIN plus order delta t square delta x square, right. And as delta t goes to 0 and delta x goes to 0, this epsilon t goes to 0. That means this equation is consistent, right. So, your FTCS scheme is consistent. There is no problem as far as consistency is concerned, but that is not enough. Let us look at the other property, let us look at the MPD. So, how do we get MPD? So, we have discussed last time that right now your FD is equal to this. So, this one is my FDE, right. So, when we are solving using a numerical scheme, we are basically solving this problem on the computer, right. So, we are solving FDE equal to 0 in our computer, right. So, FDE is basically identically 0 in our computer, that is what we are solving. That means, what we are solving is basically ut plus cux in. So, this is basically this one is equal to minus delta t by 2 utt in and plus order delta t square delta x square, right. Now, we will look at the lowest order term in the truncation error. Okay. So, in this case, this is the delta t term, which is the lowest order term, because as we have been discussing, that is what is our main concern in terms of accuracy, and also we will see here stability, right. So, we will use utt is equal to c square uxx, right. This I have derived many times. This is nothing but the extension of ut plus ux equal to 0. We take the derivative with respect to time and rearrange the x and time derivatives, and you will get this relation, right. So, this will become minus delta t by 2 c square uxx, okay, plus the order delta t square delta x square, right. So, your MPD becomes, so take all these things together, this is at n, okay, del u by del t plus c del u by del x is equal to minus c square delta t by 2 uxx, or in full form it is del 2 u by del x square, right. So, this is our modified differential equation. So, we are trying to use solve this PD using this FTCS scheme, but this the equation that we are solving is not the equation that is supposed to be that is the PD, but a different equation, right. And this equation is a convection diffusion equation, and with the diffusion term negative, right, because minus c square delta t, c square is positive, delta t is positive. So, that is why that term is negative. That means, your scheme will become unstable because it has got negative diffusion. That means, the viscosity is negative, right. So, that is why this scheme is not suitable for the convection problem. So, that is where we stopped in the last class. Okay. So, now let us look at this scheme for another problem, okay, which is the FTBS. Okay. So, your PD is del u by del t plus c del u by del x equal to 0. So, this is your PD. Apply this scheme, as will lead to your differential equation, which is basically ui n plus 1 minus ui n by delta t plus c ui plus 1 n minus bs. So, this is b I n and I minus 1 n, ui n minus ui minus 1 n by delta x equal to 0. Okay. So, this is my finite differential equation, right. So, on the left hand term, which is the FDE, we will write, expand in terms of Taylor series and write that. So, this we have already written the Taylor series here. Okay. So, we can make use of this and this, right, to get the terms. Okay. So, this will be nothing but the same as the FTCS, the first term. So, that will be UTI n and plus, let me just see what are the terms, plus delta t UTTI delta t UTTI n and plus all other terms, okay, and plus c, and this will be ui minus 1 n. So, all you need to do is that in this equation, let me write it here. okay, ui minus 1 n will be ui n minus delta x u x I n plus delta x square by factorial 2 u x x I n minus delta x cube by factorial 3, okay, u x x x I n, right. So, you can rearrange it, write u minus I minus 1 minus u I n by delta x. Okay, I will take the negative of that because that is what we want to put here. Okay, so that will become u x I, okay, minus delta x by 2 u x x I and plus delta x square by so that will be factorial 3 u x x x I n, right. So, put all of this here, this will become c u x I minus delta x by 2 u x x I n and plus delta x square by factorial 3 u x x x I n and plus higher order terms, right. This is my FDE. You will rearrange it. Okay. So, one will be del u by del t plus c del u by del x I n plus the other term will be delta t u t t I n minus c delta x by 2 u x x I n and then there will be higher order terms. Okay. So, that will be order of delta t square and delta x square. Okay. As I told you that plus minus this does not matter, all we are looking at the order of the term. Okay. So, if you look at this equation, okay, so this is my PDE, okay, and this is my FDE. So, as delta t goes to 0 and delta x goes to 0, okay, your all the truncation terms. So, this is my truncation error lambda t epsilon t, okay. So, that goes to 0 as delta t goes to 0, delta x goes to 0. So, my FTBS scheme is also consistent. Scheme is consistent. Okay. Now, let us look at the what exact PD that numerical scheme is solving. Okay, that is the modified PD. So, how do we do that? We will say that my FDE basically identically goes to 0, right. That means you can write del u by del t plus c del u by del x I n will be equal to minus delta t u t t I n minus plus c delta x by 2 u x x I n plus order delta t square delta x square, right. Use the same relation that we had u t t equal to c square u x x, right. So, this shall become minus c square delta t, okay, u x x and okay, I have to be little bit careful here, okay, so that I do not make any mistake here, and this is c delta x by 2 u x x I n. Okay, I am getting a factor of 2 somewhere. Okay, just let me work this out. Okay, so if I take this c delta x out, this will become 1 minus c delta t by delta x u x x. So, that is what I want to get, okay, but I am getting a delta x by 2 extra. So, let me just work this out, okay, just give me a minute. So, mine is u I minus 1 n the ui minus 1, and so that will give you the delta x is getting down, okay, and this is delta x by 2. Okay, there is a delta t by 2 also here. So, that is what I was missing. Okay. So, this is delta 2 by 2, this is delta t by 2. Okay. So, c square delta t by 2. Okay. So, that will become c delta x by 2 1 minus c delta t. Okay. So, this factor. Okay. So, this is also now in a convection diffusion equation form. Okay. If you can write it del by del t plus c del by del x. Okay, I am removing this I and n. So, this is also now in MPD. Okay. Remove this other part. So, this is my MPD. Okay, just let me see if I am not missing any term. Okay, this is for the differential equation. MPD, that is for FTCS. And if you go to the FTBS, okay, so that will be minus 1 minus c delta t by del x. Okay, so there is one negative sign which will come here. Okay, so 1 minus c delta t by del x. Okay, so this is correct. Okay, okay, so for this, so this is now in the form ut plus cux is equal to uxx, right, with multiply by alpha, right. For this scheme to work, for this scheme to become stable, your diffusion terms will be positive, right. So, this means you will have this thing positive c delta x by 2 1 minus c delta t by del x, okay, should be 1, right, and this is nothing but your Courant number lambda, right. So, that is basically if c is positive, if c is positive, okay, then basically 1 minus lambda okay. So, equal to 1. So, that means lambda should be equal less than 1, right. So, that is what we have been saying, that when we are trying to solve our equation using the FDBS scheme, the linear convection equation, the criteria is your Courant number or the term which is c delta t by del x should be less than equal to 1. Okay. This will be less than equal to sign. Okay. So, lambda should be less than equal to 1. If lambda goes greater than 1, then the scheme will the solution will blow up, right. And we have talked about the physical region also. That means that the distance of delta x, and you are covering c delta t for a given time, you are covering some distance c delta t, and if the c delta t is basically greater than delta x, that means you are jumping over the grid cells and you are not honoring the physical phenomenon that is happening inside that cell, and then in those conditions it is most likely that it is going to blow up, right. The same thing that we are seeing from our modified PDE also, where we see that it will only work when the lambda is equal to or less than equal to 1. Okay. So, these are some information that you get from MPDE, okay, the modified partial differential equation. So, the modified partial differential equation is basically the exact solution of the numerical scheme. It is not the exact solution of the mathematical model or the partial differential equation, but this is the exact solution of the numerical scheme, and it is different from our PDE. Okay. It is not in this particular case, for example, it is not a convection equation, it is a convection diffusion equation, both in the case of FTCS or FDBS. Okay. For the FTCS, this scheme is unstable because of the negative diffusion, and if you go to the FTBS, okay, forward time and backward space, this would is stable only when lambda, or here it is sigma, basically c delta t by del x is basically less than 1 and c is positive. Okay. So, that is the criteria. This is called Courant criteria or the CFL criteria. CFL basically there are 3 scientist names are included here. C is for Courant, F is for Fredericks, remember the Lax-Frederick scheme that we have discussed, and L is for Levy. Okay. So, that is called these three people came together to or basically derived this criteria, and that is why it is called the CFL criteria. Okay. Now, before going, I also want to do one MPD which is for the basically the diffusion equation. Okay. Although this will not give you the stability criteria, because this scheme, if you see, then if nu is positive, okay, then it will already basically you assume that it is going to be stable, but we have seen that this also becomes unstable when nu delta t by del x square is basically greater than 0.5, right. But that we will not be able to see. For that we will go to another criteria which is called the von Neumann stability criteria. We will discuss that in the next class, but right now just try to get the MPD for this particular equation. Yeah, so MPD is not made for basically getting your stability criteria, although it reveals for certain convection equations what is the stability limit and what is the what are the constants for the scheme to be stable. But a more formal criterion that tells you whether the scheme will be stable or not is your stability criterion, and that we will discuss in the next class. Okay. So, just try to get the MPD for this equation, and we have discussed so many other equations like Lax-Frederick equation, leapfrog scheme, Lax-Frederick scheme, and so many other equations, right. So, Lax-Van der Waals scheme, then you have the Crank-Nicolson implicit schemes. You can go back and basically try getting your PD for those schemes. Okay. So, del to u, okay, if I use this FTCS here, okay, so this will become ui plus 1 n minus ui n by delta t is equal to nu ui plus 1 n minus 2 ui n plus ui minus 1 n by delta x square, right. And we will do the same thing. So, this would become this is our PD. So, what I will do, I will put everything on the left hand side minus nu equal to 0, because this is our FDE, right. So, then what you can do, you can write it. So, this will become ut I n and minus delta t by 2, okay, ut t I n and plus higher order terms, okay, right. I have just derived that. Let me just see. Okay, plus delta t by 2, not minus delta t by 2. Okay, and minus nu, and if you use this expression for ui plus 1, ui minus 1, and okay, just let me write it quickly. Ui plus 1 n is ui n plus delta x uxi n plus delta x square by factorial 2 uxxi n plus delta x cube by factorial 3 uxxxi n, and so on and so forth, and ui minus 1 n will be ui n minus delta x uxi n and plus delta x square factorial 2 uxxi n minus delta x cube by factorial 3 uxxxi n. I'll write one more term, delta x to the 4 by factorial 4 uxxxi 4 power 4th derivative, okay, and that will be delta x 4 to the power factorial 4 by uxxxi n, right. So, I want to get this term, so this will be ui plus 1 n minus 2 ui n plus ui minus 1 n by delta x square, right. So, this term would, if I add a and b, okay, we are doing a plus b, right, and then we will get this term. So, this would get cancelled out, the third will get cancelled out, and that is why I had to return the fourth derivative, okay, and delta x square will get cancelled out, and this is 2 multiplied by factorial 2, that will become 1. So, that will become uxx I n, and then there will be delta x square by 2 by factorial 4. So, into 2 by factorial 4, that will become 12. Okay, this is u x x x I n, and then there will be higher other terms, right. So then this is basically u x x I n plus delta x square by 12 u x x x I n, and plus you will have higher term. So the fifth term will also cancel. So this will be delta x to the power 6. So let us for 4, right, by some factor here. Okay, and this will be del 6 u by del x square, del x 6. Okay, so this is order delta x to the power 4. Okay, and this is order delta x square. Okay, so rearrange it. So this will become u t I n minus nu u x x I n, right. This is our PD, and you can write all other terms on the right hand side. Okay, so that will become your minus delta t by 2 u t t I n, and minus that will be plus nu delta x square by 12 u x x x x I n plus order delta t square delta x to the power 4, right. Now, we will use this relation u t t equal to, so u t is equal to nu u x x, right. So, if you do u t t, that will be basically nu u x x and then divided by u t, right. So, that will become nu square u x x x, right. So, we have to basically represent the lowest order time derivative into the exponential derivative to get the MPDE, right. So, this will become minus nu square delta t by 2, and then I am collecting all those fourth order term plus nu delta x square by 12 u x x x x I n, right, and plus order delta t square delta x square, right. So, here also you can see that as the delta t goes to 0, delta x goes to 0, you get your this scheme the left side. So, your f d goes to p d. So, it is a consistent scheme, right, and this is your MPDE, okay, del u t by plus minus nu del u to u by del x square is equal to this. Okay, this is your MPDE. You can take away your I and n here. Okay, now you can do one. You can see one interesting thing. Okay, so what I am going to do? I am going to take this nu delta x square, okay, outside. Okay, so that will become, and maybe take 2 also, right. So, that will become 1 by 6 minus nu delta t by del x square. Please when you see, please take care that the signs are proper. Okay, so one thing you may note here, one is that you cannot decide about the stability of this scheme directly, because this is the fourth order dissipation term and this is the second order dissipation term, right. So, you already have the dissipation from your second order dissipation term. So, even if this term goes negative, okay, still your second order dissipation term may basically overcome and to give you stability, right. But what you can say from this equation, this is your MPD modified PD, is that let us say if you use your delta t such that delta t is equal to delta x square by 6 nu. Suppose you select your delta t such that your it is the value is delta x square by 6 nu, then this term will get cancelled out, okay, and you will get a basically a equation which is in the special discretization, this is order of delta x to the power 4, right. So, you will get an equation which is del u by del t is equal to nu del to u by del x square plus order delta t square and delta x to the power 4, right. So, you get the fourth order accuracy in your special scheme if your delta t is equal to delta x square by 6 nu, and let us say if nu equal to 1, then basically delta is equal to delta x square by 6. Okay. It does not give us the criteria that we wanted, that is basically nu delta t by del x square is less than 0.5. okay, that we have seen while trying to solve the problem, right. So, that we will get from the stability criterion, the formal stability analysis, but now you know the approach that how to get your modified partial differential equation. So, the modified partial differential equation is basically the exact solution of the numerical scheme that you are trying to solve, and the approach to get it is basically use the Taylor series, put the values in your finite differential equation, and basically make that finite differential equation goes to 0, and collect all the terms of the PD on the left. On the right hand side, you will have the truncation error. Now, look at the lowest derivative of the truncation error, okay, and that will be typically a time derivative. Convert that time derivative into the special derivative, and you will get an equation which will give you the form of the modified partial differential equation. So, for the FTCS and FDBS, we had seen that we have got the numerical diffusion. The diffusion is not present in your PDE, but that comes because of the numerics, because of the choice of your numerical scheme. Okay. So, with that we will stop here today, and in the next class we will discuss about basically what are the criterions to decide our numerical scheme for a particular problem. Thank you very much.